I got one. Hi y'all, this is Rafa Banuelos, and you're watching Biomechanics in the Wild, the channel that explores interesting biomechanics topics beyond those studied in the classroom. We've explored many interesting questions and ideas to date, and today we will be diving into growth. We've all seen the movies and imagined being bigger or taller. What forces are at play to allow giants to wander the earth? And what forces prevent those too large from existing? People and animals come in all shapes and sizes. The smallest mammal, the bumblebee bat from Sri Lanka, sneaks into the ring at 2 grams and 1 inch long, while the largest, the blue whale, breaks records, weighing up to 400,000 pounds and with lengths beyond 100 feet, making it one of the largest creatures ever. Why do some mammals break heavyweight records while others are just big enough to be visible? Today, on Biomechanics in the Wild, we will explore how big these animals can get and delve into some of the factors that constrain them. What role does size play for mammals, and why does size matter? Size serves as an important indicator on an animal's fertility and ability to have offspring. Aw man, look at those puppies. It also influences the lifespan that it'll live. That hot tub looks pretty nice too. Particularly, size is a test to its ability to survive food shortages or droughts. This is because of metabolic rate, or the amount of energy the body needs to survive and grow. That is, the rate at which organisms process energy and materials determines how fast they grow and reproduce, how long they live, and how rapidly they move through space. It's because of this principle that mice can reach higher population abundances than elephants. You see, size and changing climates affect the rate at which a certain population increases. The ancient Greeks discovered the idea behind geometric similarity. When I hear this, the first thing that comes to mind is symmetry, where all parts are equal. However, geometric similarity actually refers to how things scale with increases in size, such as forces in the bones and muscle changes in these animals. These scaling factors are not always proportional, as in the case with body mass and limb dimensions. If animals were to increase proportional to body mass, the changes in limb dimensions would not be able to keep up with the increased amount of mechanical demands of support. In contrast to geometric scaling, allometry is a difference in scaling that comes from muscles and bones growing at different rates. These differences in growth also lead to differentiation as well. As you see in the allometry plots, the left shows a linear increase where the head and body grow together with a locked aspect ratio. On the right, the head grows first and the body follows later. Allometry, coming from the root words allo meaning different and metry meaning measures, describes how these two different things come to be two completely different creatures. Following these different growth patterns, although the structure and the functions of the different bodies seem similar, the big-headed creature is clearly built different. These different proportional growths are important in large animals because they impact the size of certain bones and muscles that may support different weights. As objects grow, they gain interior volume faster than surface area. That is, they get thicker faster than surface area grows, and the stress doesn't mean linear changes in mass. More specifically, larger mammals maintain uniform skeletal stress, mostly by having a more upright posture, which decreases mass-specific muscle force by increasing the muscle mechanical advantage. The changes in limb dimensions cannot keep up with mechanical demands for support. That is, they become straighter limbs to be able to have a higher mechanical advantage. We can see this in the limbs of elephants, as they are much straighter, whereas smaller animals like the lizard have more pointed legs. Overall, as animals get larger, mass and stress don't scale equally, so other changes need to occur to support the mass. These may include changing arrangement of muscle fibers, rotating pennant angles in muscle fibers, and straightening the limb orientation. Gravity accounts for a large portion of the force that limits land mammals. When gravity is reduced and mammals take to the ocean, size constraints become more lenient. As a matter of fact, mammals need to be bigger for thermoregulation in order that they can have more cells to maintain a certain body temperature. In addition, metabolic rate and access to more food allows marine mammals to continue growing in size. I'd like to extend a special thanks from everyone at the channel and hope you can stay out on the lookout for new videos. Until then, thank you for watching Biomechanics in the Wild, and see you next time!